Good afternoon, and we're here to do an example lab of a titration. The objective of this lab is to determine the concentration of an unknown acid. The acid's identity is hydrochloric acid, so we're not so much looking for the what type of acid it is, but how concentrated is it. This system or setup has a few kind of parts to it. We have a beaker below here, which will hold the unknown. Moving up here, I have a thing called a burette. It is a glass device with very fairly accurate markings on this thing. Okay, that's the reason why we use it. Just dispense a very specific amount of material. Okay, we have our unknown, which is measured in a graduated cylinder. Currently, I have 17 milliliters of unknown there, and I have phenolphthalein, which will tell us when we've reached equivalence. Okay. First thing I would do is start filling in some of the information needed to run the lab. Okay. My burette is starting at 3 milliliters. So what I have here is a general table that I use to do this. Now the 3 milliliters is going to go right here. 3 milliliters, 3.0 milliliters. It's right on that. And I have a known and unknown. Now my unknown is going to go in the beaker below, which is the bottom, and that's going to be my acid. Sometimes I can put an A there just to remind myself. The known is going to be a base. Now in this case, that's one piece of information that your instructor will give you. My known is 0.1 NaOH. The fact that this NaOH is important here because this is going to react with the HCl to form water. So NaOH plus HCl will form NaCl plus water. So it's reacting in this HCl in a 1-to-1 fashion. Okay. So either way, my objective here, we've done a bunch of stuff with titrations already, but few things you gotta know is what is my known concentration, and how much of my unknown do I want to use in the beaker below. That's kind of an important value. These two values will be given to you by your instructor. So why do I care how much I have in the beaker below? Well, obviously the more I have in my beaker below, the more of the other individual chemical it's going to take to neutralize it. So I have my burette here, and I'm going to measure my start on this thing. Now I'm not at 0. It might say that was a mistake, but no, it doesn't make a difference. I have 3.0 here, and the 0 mark is located right here. And I'm going to dispense this thing until I finish, until I reach my equivalence. Well, if I have too much in here, then I might end up running out before I reach equivalence. So I just want to, and that's fine. Every time you make a mistake, you learn something, but I want to, for the sake of our labs, we want to make sure we don't take too much just so we don't run out. And I chose to take about 15 milliliters. And again, that volume, if you've done some practice problems here, you know that volume can sometimes tell you a little bit about the concentration of the unknown and the known relating to one another. So this is going to be 0.015, and without getting too much into it, but if this volume is the same as this one, then the moles are the same and the concentrations are the same. So you can sometimes tell what's going on here just by looking at the comparison of these two volumes. So anyway, let's get started with our titration here. Now I'm going to take and dump in the 15 milliliters, and that's in liters here. And let's just take a moment, just dump it in and add in our phenolphthalein. So, all right, so I'll take this thing here and I'll just back up a little bit here and give you a better view, hopefully. Dump this guy in here. And I'm just going to, that's my 15 milliliters. I'm just going to add in, maybe 1 or 2 drops of phenolphthalein. Now, you notice it's clear. So acids are clear with phenolphthalein. And they turn pink with bases. That's the general idea which we're looking at here. So we have acids are clear, and acids are clear and bases are pink. So what I'm going to do here is I'm going to titrate this thing until it goes from clear to pink, until that turns pink and stays pink. I don't want a real dark pink. I want just the first cyan pink to stick around for 10 seconds or so, or 5 to 10 seconds. All right, so that would tell me that I'm going to be at equivalent. So let's start dropping this in here. Hopefully you got a decent view of this. And as I drop it in, it takes a little bit of time, and you can stir, or you'll see it takes a little bit. Now, right where the liquid drops in, you may or may not have a good view of that. You'll note that it's starting to get a little bit pink right where it drops in. And it's not quite showing up yet, but it's going to become more prevalent there. Because right where it drops in, there's a huge concentration of hydroxides, and that causes the phenolphthalein to turn pink right there. Now, you notice right there, again, right where it drops in, it turns pink. And then as the H ions, H plus ions around it sort of gobble them up and neutralize them, they go away. But this is a good sign that we're heading in the direction towards being basic, or at least towards neutral and then basic. And that little pink zone will stick around longer and longer and longer. And the goal would be for that pink to, I guess to stick around permanently, at least turn slightly pink. Now there it goes, sticks around a little bit longer, starting to build up. That means my H plus ions are slowly being worn away and ended. So there it sticks around there. But if I swirl this, it'll go clear, and it does. So we'll take a moment and keep right on going. We're getting awfully close there, and the goal would be to have a couple drops determine whether this thing is pink or whether it's clear. Now, for our learning purposes here, I'm not too worried about this, but we'll do our best, and you'll see it stick around. You can always be patient and wait it out a little bit. All right, and just do the last couple little bit here and see if it sticks around. And just turned clear. Let's go a little bit more and see if she stays pink. And looks to me like it's pretty pink. It might not stick around forever, but to me that's about as nice as it gets, and it's going to eventually turn back clear. It's right on the edge, so great. And I could record my volume down here, which is now going to be 28.9. So let me record that down so I don't forget. And I got here 28.9. Now again, I could continue at this point if I wanted to and just say, what would happen if I add a couple more drops? Just a little bit more, and this thing should just turn nicely pink. Okay, and it's doing the same thing it's doing. So all it's going to do by adding more is just get more and more pink, which means we're getting more and more basic and beyond our equivalence point. So, but many times kids will have this color when they're done titrating too. That's fairly acceptable for beginning here. So now let's walk through the calculations here. So the first thing I want to do is I have this table here, and I like this table, but the table here we have is really just a data table. So you must show work about how you're getting things. Each table represents a molarity formula, so let's do it right here. So molarity equals moles per liter, and right now I've added as many hydroxides and H pluses so they matched and knocked them out. So these two are equal at this point. The original H pluses in there are now equaling the amount that we added. So this volume, subtract the 2 off, and we get our volume. 28.9 minus 3 is just 25.9. If I can do that in my head. Okay, 25.9. All right. So that's the amount that I actually dispensed, which is really important. That's the amount that entered into the beaker. So this is going to be 0.0259. Now we're going to solve for the moles here. So I'm going to plug that into my formula here. Molarity times liters equals moles. So I'm going to multiply these two together to get my number of moles. That's going to be 0.1 times 0.0259, and this is going to give me, move 1 over, 0.00259, and that's going to go right here. So that's the moles, the actual base that I emptied in there. All right, so I got 0.00259. At that point, that equaled these guys, which is 0.00259. Now, keep in mind, there's no acid left, and there's actually no base in there either. These were eating each other, neutralize each other, so they're gone. They formed the products. I had originally 0.00259 moles of this. I added 0.00259 of this, and now they're both gone. And I now have 0.00259 of this, and I made 0.00259 more of that. They're both neutral. So my goal is to determine the original concentration of my original solution, which is this guy right here. Now keep in mind, I destroyed my sample while I made it, but when you are testing something, maybe you're going out to a lake and you got yourself a little boat and you're out in this boat and you're just fishing around a little bit here, you take out and you grab a sample of water out of the sample and you bring it back and you test it. So the sample I have, this 15 milliliter sample, is representative of my larger sample, or hopefully it is. So I destroy my sample by finding out information about the original contents of that solution, which is pretty common in testing, that it gets sort of destroyed while it's being tested. So now I have my moles of my original acid, and I want to divide that by my moles by the volume of my original acid to get the original concentration. And let's do that right here. Let's just do it right here. So I have 0.00259. Hopefully I'm not going into my video here. Divided by 0.015. And what is my new concentration? Now you notice that in this case we have equal moles in a smaller volume, means that this guy is more concentrated than this one. So my number has to be bigger than 0.1. Same number of moles in less volume. Now if it were, this is looks like about 26 milliliters here. If I had 13 milliliters, it would be twice as concentrated. So there is a little bit of reciprocal relationship here that you kind of want to be aware of. This is 15. If this was 30, it would be half as concentrated. But let's do the math here. Just divide them out, and let's see what our actual answer is. 0.00259 divided by 0.015, and I get 0.17. All right, so, and that is the answer here. 0.17 is my concentration, and that answers my problem. Okay. Let's recap again what happened here. Let's go to a new screen here, and I'm just going to draw a little beaker right, so I got some room here. So I had a beaker in here with a certain amount of H pluses in it, and I didn't know how many were in here. There's H plus, there's a cation and there's an anion. There's a bunch of them, and the cation is H plus ions, and there's a bunch of them. I don't know how many I have, but I'm dropping in hydroxides in here, and for every hydroxide I drop in, my solution gets close, starts acidic, and is reaching upwards pH towards 7, and it will go towards the basic range if I let it. But I had a bunch of these in here, and I didn't know how many were in there, and there's anions too. But as I add them in, they got knocked out, so I added in one, knock it out, added another one, knock it out, and I start creeping every way closer and closer to neutral. Added another one, knock it out, added another one, knock it out, and all of a sudden, ding, 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 this thing hits right on the, it's not perfect, right on the edge here, and I knew how many I added, If I know how many I added, then in the end, I knew how many were there to begin with. If I added 4, there were 4 originally. Again, what does this beaker look like now? It would just have 4 water molecules. It have water that I got produced. Every time I drop one in, I get a water molecule, another water molecule, and another water molecule, and another water molecule. Of course, I also have the cation, anion, NaCl, and I'd have 4 of those as well. Okay, so that's what happened in the beaker, and our overall objective is determining the concentration of the unknown, the original concentration. And we'll end there. Thank you.